This program is brought to you by Stanford University. Please visit us at stanford.edu.
Now, Liouville's theorem is really at the heart of classical mechanics. It's at the heart of Hamiltonian classical mechanics, and a quantum mechanical version of it, which is called unitarity, is very much at the heart of quantum mechanics. It will profit us to understand Liouville's theorem because, as I said, it is the immediate classical analog of one of the most fundamental principles of physics, quantum mechanics. It can also be thought of as the idea or generalization of the idea of information conservation. We talked about this, I think, in the first lecture, where, let me just remind you, I think I've done this a couple of times, but let me remind you again, that if you have a phase space which consists of a collection of points, now by the phase space I simply mean the space of possible configurations of a system. In the case of a mechanical system, it would be positions and velocities. In the case of just a system with a finite number of states, it would be any one of those finite number of states. And then the laws of mechanics for this very simple setup would simply be expressed as a rule for going from any configuration to any other configuration. And I can draw it in a more complicated way, but there's not much point. I could draw it so that the lines cross, but that doesn't add anything to it. You could have some disconnected cycles, but generally that's the pattern. And you'll notice that each point has one arrow coming into it and one arrow going out of it. That's the basic idea of information conservation, that nothing gets lost. There's no, let's call it convergence or divergence of the flow in the phase space. This can be thought of as a kind of flow. What's the word for what they do in discos where they flash lights at you? Stroboscope. Strobe. You could think of it stroboscopically, where each instant you flash and the system moves to the next configuration. So it's a sort of stroboscopic flow of the points in the phase space. But you could imagine populating each of these points. Populating means imagine a system at that point in phase space undergoing the motion that the system is supposed to have. So we would have a collection of systems filling up the phase space, one at each point in the phase space. And as time evolves, the points in the phase space just move. How to describe this? I think probably the best way to describe it is that they move incompressibly. Among other things, that means that if you start with a separate point, a separate system at each point in the phase space, you'll never wind up with 2 points or 2 systems at the same point in the phase space. It's not like playing Monopoly, where the Monopoly men can wind up on the same square. That never happens. They stay distinct from each other, the points in the phase space. They don't diverge, they don't converge. What would diverge mean? Diverge would be a situation where an incoming line would split in 2. Now, what would that mean? That would mean there was some ambiguity in the evolution of the system. If it went from here to here, it wouldn't know where to go next. Sometimes it might go this way, sometimes it might go that way. That doesn't happen. So there's no divergence of the flow, and there's also no convergence of the flow. Convergence would mean that from 2 different phase points, you come to the same phase point. Then you would always know where to go, but you wouldn't know where you came from. If you found yourself over here, you wouldn't know if you came from here or over here. Those are the forbidden kinds of flows. As I said, you can think of a lack of convergence or divergence on the phase space. Yeah?
Even if you have it where it diverges, but if it diverges under a statistical law.
It's quite thinkable. It's not that it's not thinkable to have these things. They don't occur in classical physics. They don't occur except insofar as you ignore things, except insofar as you ignore degrees of freedom. As I've said over and over, friction is an example where you start a system in any number of ways. You can start in many ways, it comes to the same configuration. Well, not quite, but you get the idea. Friction just slows things down, brings them to rest. No matter how they start, they come to rest. Many, many different configurations can wind up exactly the same, but that's only because you've ignored things. You've ignored the molecular structure of a tabletop. You can take this as an experimental fact, or you can take it as a consequence of the basic rules of quantum mechanics, but all the classical mechanical systems that are of interest in fundamental physics have the property that there's no divergence or convergence. Yeah?
Is that saying something more than classical mechanics is based on differential equations and there's unique solutions?
Yes, it is saying something more than that. It is saying something more than that. And we'll see what it says. It's what Liouville's theorem is what it says. But we'll come to it. For example, the sort of thing that can't happen is, here's phase space, okay? Every point in this phase space is distinct from every other point in some sense. Now you could take a group of points and follow them, and they might all squeeze together into a smaller volume. All right? That's the kind of convergence that doesn't happen. Instead, the flow in phase space is a kind of incompressible flow, both incompressible, what's the opposite of compression, and non-divergent. Well, this phase space doesn't blow up, it doesn't shrink. But we'll come to the precise definition of it soon enough. So in some sense, the phase space doesn't pinch together or diverge. It's as though, here's the way you can think about it. In the continuum mechanics case, you can imagine populating the phase space, let's call it P and Q, Q and P. And of course, there may be many P's and Q's. I simply can't draw them on the blackboard. And we might imagine in the same way that we populated each point here with a system, we can imagine populating the phase space with a dust of points. And follow that dust of points. Let's assume that the phase space is populated uniformly with a constant density, a uniform density of points, of dust. And we follow each point as it moves through the phase space. It defines a kind of flow. But it defines a special kind of flow which is called incompressible. And it basically has the property that each point in the phase space can be thought of as having a little volume around it. Each one occupies its own little volume. If we take the density to be uniform, then each one of these volumes is the same. And as we follow it, when we see it later, each phase point is separated from each other phase point by the same amount of volume in the phase space. Right? Or you can say it another way. If you take a group of points, there are three ways to say it, all of them equivalent. The first is to follow individual points with little volumes around them and watch them move. Okay? The volume of each little point, or the region occupied by that little point, stays the same. But we can generalize that. We can say take any region of the subspace, of the phase space to begin with. Take any region and follow its points. Follow its points with time. After time, that phase space region will change. It'll change its shape. Some points move faster than other points. It may spread one way, it may stretch some direction, it may compress in another direction, but the one thing that's true is that the volume of that region will stay the same. In other words, the volume of a fixed set of points in the phase space will not change. And it will maintain connectedness. And it will maintain connectedness, absolutely. They don't disconnect. The connectedness is simply the predictability. If it became disconnected, how could it become disconnected? A phase point would split somehow, which would simply mean it didn't know where to go. The equations broke down at this point and didn't tell a phase point where to go properly. So, yeah, regions maintain their connectivity. In other words, a region like this can't break up into two disconnected regions. And a hole cannot appear. So it's a very continuous, smooth, no holes. The connectivity is conserved, but the type of connectivity, simply connectedness, multiple connectedness, whatever it is, the topology of the chunk of phase space is maintained, as is its volume. What is not maintained, in general, is the distance in the phase space between points. Take a pair of points in the phase space and follow them. If we follow them, we may discover later that they're closer together. Now you say, how is that consistent? How is it possible that the volume of a phase region doesn't change, but the distance between points can change? Well, what can happen, for example, is a volume can stretch in one direction and compress in the other direction. The volume being conserved. The volume of all of this collection of points in here is unchanged, but if you follow each point, you'll find that the shape changes, but the shape changes in a way that leaves the volume unchanged. But in particular, this point and this point are now found here and here, so they're much further from each other than they were. On the other hand, this point and this point are found here and here. So they're much closer together than they were. Points switch? No, everything is extremely continuous.
But is it conserve orientation?
Conserves orientation.
How do you move past each other?
What does that mean? Oh, you mean can one, well, you can certainly have a situation where there's a point in phase space moving to the right and another point in the phase space moving to the right, and they start like this, and this one is moving faster than this one and passes it. Yes, that can happen. No question that can happen. For example, you can have a situation where if you started with a square in phase space, that square could evolve into a, what is that called? A parallelogram of the same area. That would happen, for example, if the top was moving faster than the bottom, but the width of the whole thing, that's a sort of shear motion where the top shears relative to the bottom. That's perfectly allowed. That conserves the volume. If the height and the width stay the same, conserves the volume. So that's possible, and that would certainly allow a point back here to get ahead of a point over here. Yeah, so well, go ahead, ask the question. Yeah. What's that? Yeah. The double pendulum and the gravitation. Yeah. Absolutely. Absolutely, but we'll, yeah, we'll talk about that case. That is not a counterexample to this, right? It's an example of it, but one which is less smooth and less predictable, but for reasons we'll come to. Okay. Well, let me just say it very quickly. I say the phase space maintains a certain degree of connectivity. It maintains its connectivity. All that happens is shape changes, but the shape can change wildly. For example, this sphere can evolve into something with, I'm trying to keep the volume the same as it was before, but I'm probably not. You know, horrible. So there's no rule that says that the shape can't evolve into some wildly, extravagantly different structure, which eventually starts to look more and more fractal. Now, it never really forms a fractal because continuity tells you that things which are close to each other will stay close to each other, but in time it'll start to get more and more fragmented, more and more fractured, but always maintaining its volume, okay? Maintaining its volume so that distinguishable points remain distinguishable, and a measure of distinguishability is the volume surrounding a point. But we will return to this particular picture. I ought to leave it there because I'll probably wind up drawing it again, but not right now. That, incidentally, is the basic case of a chaotic system. Chaotic systems do exactly this kind of thing. Non-chaotic systems tend to maintain a greater degree of shape coherence, we can call it. Say it again? No, they don't. They don't stay in close proximity. No, no, no. The statement is the volume of the region in phase space is maintained. So what that tells you is that if 2 points do diverge, or let's say that if the phase volume stretches in one direction, it must compress in the other direction. Okay? So it's not completely without rules. But the only real rule is that the phase volume is maintained as time evolves. Volume means the same thing that it does in calculus. It means the integral. It means break up the region into a lot of extremely small cells. Let's talk about area for the moment. Let's not try to get to higher dimensions for a minute. Let's just take the case of 1Q and 1P. Then what I mean by volume of phase space is just the area of the region. Regions have area irregardless of whether they're squares. They don't have to be squares or rectangles to have area. You have to use a little bit of calculus to add all of these up, but there's a well-defined notion of area. And as you follow it, the shape may change, but the area doesn't. Now, if it's a higher dimensional system with more than one P and Q, incidentally, as always, there's one Q for each P. They come in pairs. But we simply have to think about the higher dimensional version of volume, where we break up the volume into lots of little cubes, count the cubes, and add them up. Yes, Michael?
I think it's worth pointing out that points that are nearby in phase space have both similar, they're close by in position and close by in momentum.
Yes, absolutely. That's right. Nearby means close by in position and momentum. But it doesn't mean that they stay close by. Okay? And in particular, the chaotic case is the situation where there's a great deal of tendency for points which are close to each other to diverge from each other, but always at the expense of compression in some other direction. Yeah.
I'm thinking of throwing dice.
Yeah.
They're tumbling free in space. Then they get a table and under the influence of gravitation, and one of 6 possibilities comes up.
Right.
So there's no way of having that happen without friction.
We're having which happen now?
Having a free tumbling system mapped into a system that's like.
Oh, you say, well, yeah, that's basically friction. You say there are many ways to start, and you can wind up with a 6 on the table. Yeah, right. If you didn't have friction, it would just bounce off the table and rebound, and
It wouldn't stop.
it wouldn't stop. Yeah, yeah, right.
It's pretty common.
Friction is incredibly common, right? Yes, yes. And when you're doing a mechanical system in practice, if you're an engineer, you don't want to forget friction. If you're a physicist, you often want to forget friction. You want to pretend it didn't exist. In fact, in many situations, microscopic physics doesn't have friction. If you really follow every degree of freedom of a system, then there's no concept of friction in the equations. Friction is a collective effect of many variables, some of which you just decide I'm going to ignore. So it's a thermodynamic idea rather than an idea of basic mechanics. Of course, they have to be consistent with each other. When you decide not to look at a collection of degrees of freedom, the behavior of it may nevertheless reflect the fact that in some bigger sense, the phase space volume is conserved. Energy conservation is one which you might not realize if you were sliding around things on the table. So energy is lost. Kinetic energy. There's no potential energy. It doesn't go up or down. Kinetic energy is just lost. Looks like energy conservation is wrong. Those who would believe in energy conservation would make a prediction. And the prediction would be that if you very minutely and carefully measure the temperature of the table will go up a little bit, and if you know the specific heat of the table, then you can find out how much energy was absorbed by the table, et cetera, and the conservation of energy will tell you that there must have been degrees of freedom that you ignored. The same is true of this conservation of information. If you discover a system which looks like the phase space is contracting, it means you've left things out of the system. Now, that's an empirical fact in the sense that it has always proven to be the case. But by now, it is a fundamental fact derived from quantum mechanics. But let's take it as a, well, we're not going to take Liouville's theorem as a given. We're going to prove it. But we're going to prove it from something. We're going to prove it from Hamilton's equations. All right, so the beauty of the Hamiltonian form of mechanics is this flow picture. A flow in phase space, a very predictable flow in phase space, where the points move in a very characteristic kind of way, and that characteristic way is Hamilton's equations. The entire flow is determined by a single function of all of the p's and q's. If you know that function, then you know the flow on the phase space. And if you started a little boat sailing on the flow, which means you start a system at a particular point in the phase space, that Hamiltonian flow will tell you where it is at any future time. Okay, and that flow is incompressible. But let's first define the flow. So this is dynamics as a flow in phase space, as a kind of fluid flow. All right, so every point has associated with it a motion that depends only on where you are. And a motion means a time derivative. This is p, this is q. It means a p dot and a q dot. In other words, a velocity, but not a usual velocity, a velocity in phase space, consisting of the ordinary velocities, which are the q dots, plus the p dots, which are the time derivatives of the p's. Okay, so we just write down Hamilton's equations. P sub I dot is equal to minus dh by dq sub I. Notice they come in pairs. Is plus dh by dp sub I. That's it. That's all of mechanics in a nutshell in the Hamiltonian form. Okay. All right. Let's consider what it means for a flow to be incompressible. What we're ultimately going to prove is that this flow is incompressible. Okay. What exactly does it mean? Let's start with a one-dimensional flow and see what it says. So a one-dimensional flow just means you have a line, and let's populate that line with a uniform distribution of points. For simplicity, I'm taking a uniform distribution. That means that the density of points is the same everywhere along the line. or equivalently, the little tiny separation between points is uniform along the line. What kind of motion constitutes incompressible flow? Well, basically, there's only one kind, and that's just all the points move together with exactly the same velocity. What would happen if the velocity varied from point to point along here? For example, suppose it went faster over here than over here. Then there would be a clumping up of points in between. Okay? There would be a clumping up and an increase in their density. All right, but let's consider the mathematics of it. What's that? Yes, but let's just talk about flows for a minute. For a minute, let's forget phase space and just talk about the general concept of an incompressible flow. And we'll come back to phase space as a special case. That's right, you're right. But nevertheless, it's possible to think of incompressible flows in one dimension. They're very trivial. You can have any velocity you like, but the velocity has to be completely uniform all across the line, otherwise there's a clumping. Now you can think of it in two ways. You can either say, take a set of points and follow them. Let's take a connected set of points like this and follow them. One way of saying incompressibility is just that the volume of that particular set of points stays the same. All right? That's a view of it following the points. There's another view of it which stays at a particular place in space. Let's say we stay at a particular place in space. In other words, a little volume. We're not going to move that volume, but points are going to come into it and points are going to depart from it. If the fluid is moving to the right, of course it could be moving to the right in some places and the left in other places, but let's count all velocities as positive to the right. If the fluid is moving, then some points leave this region and some points enter the region. To say it's incompressible says that the number of points that enters is the same as the number of points that leaves in any given time interval. What is the condition for that? Well, it's more or less obvious that if the velocity, let's imagine that the velocity is fast over here and slow over here. All right, then it's quite clear that the number of points that are exiting the region is proportional to the velocity at this end. All right? Let's call this point 2 and point 1. Right? The number of points exiting will be proportional to the velocity of the points to the right, and that we can just call V2. That's the number of points exiting. The number of points entering is the velocity at 1. So the net increase, shall we take increase or decrease? Let's talk about the net decrease. The net decrease in points in this volume here is going to be proportional to V2 minus V1. Actually, it's V2 minus V1 times the density of the points. But as long as the density is uniform, then we can just write that the, yeah.
If the velocity is higher, the density's got to be changing.
That's the point. That's the point. That's exactly the point. Wait, if the velocity, yeah. If the velocity is higher at this end, or whichever way, if the velocity is bigger at one end than the other, then the density inside has to be changing. Incompressible means that the density is not allowed to change. Okay? So what it says is that V2 minus V1 must be equal to 0. That it cannot be a gradient or a variation of the velocity. This must be equal to 0. Now, if I take a small interval, let's imagine that this is a small interval, then the difference of the velocity at 2 and 1, assuming everything is nice and smooth and differentiable, that calculus applies, for a small interval, we can say that the difference of the velocities is just proportional to the derivative of the velocity with respect to x times some delta x, where delta x is the interval here. Right. And then we would write that this has to be equal to 0. Delta x is just a small interval. It's not 0. It's just a number. So it follows then that the derivative of the velocity with respect to x must be equal to 0 for for an incompressible fluid, which is what we would intuitively imagine, that the whole fluid has to move together. Since all of the motion is along the x-axis, I'm going to write this as the derivative of the x component of the velocity. There is only an x component of the velocity, but just to use a notation which will generalize, I'll write that this is dvx by dx is equal to 0. That's the condition in one dimension for an incompressible fluid, and it is very trivial. Questions? Good. All right, now let's move on to 2 dimensions. I'm going to call the 2 directions x and y. Why not? X and y. Now let's ask, in a small interval of time, what is the increase or the decrease? I guess v2 minus v1 would be the decrease in the number of points. What is the decrease in the number of points in this little square here? Let's take the square to be of size delta x and delta y. It's not a square, it's a rectangle. How many points are entering and leaving from on the various sides of this rectangle? All right, let's start with the number of points coming in here. Again, we're imagining that the density is completely uniform. So the number of points per unit area to start with is completely uniform. If it's incompressible, then the number of points per unit area must stay the same, must be exactly the same afterwards. So, okay, so how many points come in from this side here? Well, the number of points coming in this way per unit time is clearly going to be proportional to the x component of velocity, the y component of velocity. A velocity in the vertical direction will not contribute to points crossing this boundary here. So the x component of motion here, Vx, at the left-hand end here, will constitute the incoming points coming in from the left vertical side of the square. What about the number going out? Oh, there's another factor. There's another factor. Anybody know what the other factor is? Delta y. Yeah, the size of the y interval here. Obviously, the bigger the y interval for a given velocity, the more points will enter there. So there's another factor, which is just delta y. Now, how about the number of points going out on this side? That's also proportional to Vx, but Vx at the displaced point. All right, so we have to move ahead a little bit and subtract the points coming out on this side, exactly what we did over here. The answer is going to be the derivative of Vx with respect to x times delta y times delta x. Where does this delta x come from? The difference of the velocity here and here is the derivative of v with respect to x times delta x. All right? The difference between the x component of velocity on the right-hand side of the square and on the left-hand side of the square is the derivative of v with respect to x times delta x. We have to multiply that by delta y to find the net number of points coming through this, coming into on this side minus out on this side, and that's this. Okay, so this is the net number of points coming into the rectangle through the vertical edges. Now what about the horizontal edges? The horizontal edges, things can also move in, but now the x component of velocity is not relevant to particles coming in this direction. Only the y component of the motion is relevant on the horizontal boundaries. So how many particles come in from the lower end? Well, that's going to be v sub y at the lower end times delta x. But then we have to subtract off v sub y coming out of the top end here in order to find the difference of the incoming points and the outgoing points on the bottom and top. So that will give us the derivative of Vy with respect to what? With respect to y, because we're going from bottom to top. times delta y. The whole net change in the number of points in this rectangle is simply proportional to delta x, delta y, that's just the area of the little region, times a quantity which is called the divergence of the velocity field. This is the velocity field. It can vary from place to place, but it's definite and it's fixed. And this is derivative of Vx with respect to x plus the derivative of Vy with respect to y. If this is positive, it corresponds to a decrease in the density. What if it's an incompressible fluid? If it's an incompressible fluid, then the net number of points coming in and going out must add up to 0. All right. We can forget the delta x times delta y. That's just a number for a little area. And so the condition of incompressibility is that the divergence of the velocity field is equal to 0. Let's drop this factor here. It doesn't do anything for us. dvx by dx plus dvy by dy is equal to 0. This is not a general rule about all possible flows. This is a rule about incompressible flows that start with uniform density and maintain the uniformity of the density. Notice that it does not say that the velocity can't vary from place to place, but it does say that if the velocity is increased, if the x component of velocity is increasing in one direction, then the y component must be decreasing in the other direction. So it does not say that the velocity can't change from place to place. It doesn't require the motion to be just rigid motion. More complicated kinds of things can satisfy this kind of flow, but it is constrained in this way. Okay, questions? Yes. Yeah, but we take an instantaneous photograph of it, and we ask, at this instant, what's the time rate of change of the number of points in here? So at any instant, something which is coming in here, yes, it could turn around and go up here. That's perfectly acceptable, but that will be at a later time that it'll be found going out here. So we imagine a snapshot. Instantaneously right now, what is the time rate of change of the number of points in this volume? Okay, so if a point is coming through here, it's not going out there. Okay.
So that argument applies to free space also?
It applies to any number of dimensions. So in any number of dimensions, we could write, there aren't enough letters in the alphabet, but X, Y, and Z here just refer to a general space having nothing to do with mechanics, just a general flow in any number of dimensions. The general rule for an incompressible flow would be that the derivative of the ith component of the velocity with respect to the ith x is equal to 0. All right, that's also written in the notation sum of I. Thank you. That's also written in the notation that the divergence of V is equal to 0. Divergence simply means this act of differentiating the ith component with respect to the ith coordinate and summing them up. And it's called the divergence. Yeah. I've assumed uniformity of the density, yes. Yeah, if I hadn't assumed uniformity of the density, I just did that to make it simpler. Had I not assumed uniformity of the density, what you would have to do is invent a new quantity, which is the density at any point times the velocity. And then that would be the thing which would have 0 divergence. But if the density is uniform, then that factors out. So just for simplicity, I imagined that the and after all, if it's an incompressible fluid, it stands to reason that its density is everywhere the same, since you can't change its density. So let's come back to phase space. What are the x's The x's are just the coordinates in some space. In the case of phase space, the coordinates are the p's and q's. Right? The p's and q's are the coordinates, so we should identify the x's not just with q, but with a p and a q. So the number of x's is twice the number of q's, one x for each p and q. That's the space we're dealing with. If there's only one q, then it's a two-dimensional space, one p and one q, and so forth. All right, what are these quantities over here, p sub I dot and q sub I dot? Those are the local velocities in the phase space. They are the v sub i's. I now goes from 1 to 2n. It runs over all of the coordinates in the momenta. But these are, we could call this here, we could call it v p sub I, the velocity along the axis p sub I. This we could call v q sub I. So the p dots and the q dots are the things that are being called the velocity. Now let's calculate the divergence of the flow. We're going to calculate the divergence of the flow, and of course what we're going to use is Hamilton's equations to see that the divergence of the flow is exactly 0. All right, so the divergence of the flow, we take v p sub I and we differentiate it with respect to p sub I. So let's write the divergence of the flow over here. First of all, we have derivative of the p. I'm not going to bother writing the I. Well, maybe I should. No, let's just do it for 2 dimensions first, then we'll come back and talk about it for any number. Derivative of Vp with respect to p, with only 1p and 1q. What is that? Well, that is equal to the derivative with respect to p times Vp, but Vp is minus the derivative of h with respect to q. All right, that's the first term. What's the second term in the divergence? The second term is just dvq by dq. All right, what is vq? That's over here, plus dh by dp. So this becomes d by dq of plus dh by dp. If we have several coordinates in momenta, then we would put an I here and sum over I everywhere. Also in the lower equation here. I won't bother with it though. Well, now you can see what happens. Partial derivatives can be interchanged. The derivative with respect to p of the derivative with respect to q is the same as the derivative with respect to q of the derivative with respect to p. dp dq is the same as dq dp. It doesn't matter which order you differentiate something in. Right? This one has a minus sign. This one has a plus sign. So these cancel in pairs. They cancel in pairs. In fact, it's not just that the divergence is equal to 0. It's equal to 0 in a special way where they cancel in pairs. But that's okay. The divergence, the sum of these, dp that's exactly equal to 0. Okay? So the sum of these, add them together, that's exactly equal to 0. And that proves that the flow in phase space is incompressible. That is quite a profound theorem about mechanics, the incompressibility of the flow, the fact that the phase points can't get squeezed into a smaller volume, that they maintain sort of, they have elbows and they keep from running into each other. That is probably the most important fact about Hamiltonian mechanics, that it is this incompressible kind of flow. Let's concentrate for a little while on two dimensions, one P and one Q. Remember, this does not say that the distance between points stays the same. As I said, what it says is that the volume of a region of phase space stays the same. So a region like this could flow into a region that looks like this, as long as the volume stays the same, and in particular, 2 points which are fairly close can get fairly far. So there's no conservation of the distance between points in the phase space, only the volume of a patch of phase space. This idea that, let's take the two-dimensional case, that area is the important thing and not distance, you can see in another way. Let's take the world's simplest mechanical system, a particle moving along one axis with an energy which is x dot squared, a kinetic energy which is x dot squared over 2. I have even gone so far as to set the mass equal to 1 to make it simple. All right? There's a canonical momentum, p sub x, which is equal to the derivative. This is the Lagrangian. Lagrangian is x dot squared over 2. The momentum canonically conjugate to x is the derivative of the Lagrangian with respect to x dot, and that's just x dot. Now, I could have used another coordinate. I didn't have to use x to describe this system. What would have happened had I used 2x? Suppose I defined a new variable. Let me call it y. It does not stand for another axis. It just stands for another representation of exactly the same physics. A new coordinate I'll define, and let's call it alpha times x. Alpha is just any number, fixed. It could be 2, it could be a half, it could be 7, whatever it is. This is just another representation of the same system where it's been labeled by a different axis, or an axis with either closer or further points, different units. It really comes down to a unit transformation. Okay, what is x dot? X, first of all, is equal to y over alpha, and x dot is just equal to y dot over alpha. Let's rewrite the Lagrangian. The Lagrangian doesn't change. The Lagrangian is the same numerical quantity no matter what coordinates we use. The Lagrangian will now become x, it's still x dot squared over 2, but that becomes now y dot squared over twice alpha squared. I've just written that x dot squared is y dot squared over alpha squared. That's the new Lagrangian. It's just another description of exactly the same system. What is the canonical momentum conjugate to y? Well, it's dl by dy dot. P sub y is equal to y dot over alpha squared. Okay, let me now write, right over here, we have y equals alpha times x. We have py equals y dot over alpha squared. But that's also equal to x dot over alpha. I've used that y dot is equal to x dot. Let's see, what have I written? Yes, y dot is alpha times x dot. So wherever you see y dot here, just stick alpha times x dot. That cancels one factor of alpha. All right, but this is also equal to p sub x over alpha. All right, so let me combine that with this equation over here. P sub y is equal to p sub x divided by alpha. Notice what's happened. When you make a coordinate transformation that stretches the x-axis, it shrinks the p-axis. Sorry, yeah. If you make a transformation which stretches the x-axis, remember now, x and y are not different directions of space. They're just different coordinates describing the same thing. This is a coordinate transformation. Y is equal to alpha x. Along with it goes a transformation of the canonical momentum, but in the opposite direction. If you stretch the x-axis, you shrink the p-axis. Okay? That means, for example, if you take the phase space, we can represent it either in terms of x or y, and we take a little region, let's call this x and px. Suppose we represent that same system in terms of y and p sub y. Well, the width of this box as measured in y units is alpha times as big as it was in x units. But on the other hand, the height of the region is 1 over alpha times what it was in x units. So whether the height of this box and the width of this box as measured in either x or y are not the same, but the area of the box as measured in x and y are the same. This is a characteristic feature of classical mechanics, that the various coordinate transformations that you would do, if combined, you do some coordinate transformation, but you also calculate what happens to the canonical momenta, what you'll find is that areas in the phase space always stay the same. So the idea of an element of area in phase space is very fundamental. It, of course, comes up in quantum mechanics. In quantum mechanics, it's basically, roughly speaking, the statement that there's a smallest area in phase space. A quantum of area in phase space, we'll come to that, but not, I'll just mention it now, that things cannot be localized in the phase space better than that quantum of area. How big is the quantum of area? Planck's constant. No, not squared. Not squared. Planck's constant is not a measure of delta x or delta p. It's a measure of area in the phase space. Okay? And it says that there's a fundamental unit of area in the phase space and that you cannot think of anything smaller than that. That's the uncertainty principle. Yeah, question.
If you consider any possible evolution of a system,
Mm-hmm.
can you use that as a if it's convenient, can you always use that evolution as a change of coordinates?
Absolutely. Absolutely. The mathematical statement is that the time evolution of a system is a canonical transformation.
What
Yeah.
if you were to start with a Hamiltonian that didn't conserve energy, like a ball falling to the earth?
That did or did not?
What?
Say it again.
You start with a Hamiltonian that does not conserve energy, like a ball falling to the earth. You ignore the Earth's movement.
Why does it not conserve energy?
Because the ball picks up energy as it falls to the earth.
No, it loses potential energy, gains kinetic energy.
Yeah, okay, that's a simple. I don't know why I was thinking that.
Right. Good. Okay. So let's. All right. The statement that the flow in phase space is incompressible, that's called Liouville's theorem.
So, what you just said a while ago, it was sort of like the alpha can now represent the time dependence of the system as a point news.
Where? Here?
Yeah.
No, this wasn't representing the time dependence of anything. This was just two different sets of coordinates. That's all.
It could. And you would
No. Well,
Is that what you call a canonical transformation?
this is a canonical transformation.
Okay.
Yeah. Yeah. Right. And we haven't discussed that at the moment, but the answer is yes, that is a canonical transformation. All the interesting transformations of mechanics are called canonical, but we haven't defined them yet, so let's all right, let's talk a little bit, since it's been raised, about what chaos means. That's right.
What does it mean?
It means the area. In quantum mechanics, it's of course connected with the uncertainty principle.
It has units of action.
That's right.
So what we understand is that you mean if you multiply a p and a q, a p dot and a q dot.
A p dot and a q dot?
Yeah.
A p dot and a q dot. You want to multiply a p dot times a q dot.
Oh, that's what the two little arrows are.
Okay, let's multiply a p dot and a q dot.
That means that's independent of the values that you get. Doesn't change if you change coordinates.
What doesn't change is delta p times delta q, the area of a little region of phase space. It doesn't change. You have x and p sub x, and you have some other coordinates which you can call y and p sub y. And if you calculate take a little region of area here, break it up, and calculate its area by adding up the squares and giving them and assigning them an area delta x times delta p sub x, or add them up by assigning them delta y times delta p sub y, you'll get the same answer. So it's the area element, the size of an area, which will be the same in whatever coordinates you use, whatever coordinates and momenta, if the coordinates and momenta come from the same Lagrangian. Okay, so yes, so area has an invariant meaning in the phase space. It takes on its sharpest physical meaning when we get to quantum mechanics, where it really corresponds to the uncertainty principle.
So what would they have thought of it meaning before quantum mechanics?
Well, I don't know. What does it mean? The fact that it's conserved means that it's useful. Yeah. It tells you what the right probability measure is on the phase space, that an invariant probability measure on the phase space, and that's useful in statistical mechanics.
I see, so it partitions up the possibilities
Yeah,
of the system.
yeah. And for example, if you have some chaotic system, there's a phase space, and that means the phase point moves around and gets, really moves around in some wild way. And you ask how often, or what is the probability that it is found in a little region of phase space, then the answer will depend only on the area of the region of phase space. So area would be the thing which would tell you the relative if you are interested in the relative probability, probability could mean the amount of time spent in this little region here. The phase point moves around, blah, 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 goes crazy. We stand there and watch it and ask how much time does it spend in that little volume. That's a measure of the probability that you would find it in that volume versus this volume. All right? The answer is that the relative probability of being in two different volumes of phase space is simply the ratio of the areas. Right.
That's for a chaotic system.
For a chaotic system, yeah, for a chaotic system, yes. Right. Hmm? Well, here I'm defining probabilities not by expectations, your naive expectations. I'm defining it by the amount of time, integrated time, that it spends in a region. So that's a stronger, yeah. Right. The amount of time that it's in here divided by the total time that you sample the system tends to a finite limit for chaotic systems, yeah. Right.
So you're assuming that
No, yes, no, it probably does, but I have to think about it.
is chaotic is sort of the same thing as stochastic?
No, I'm not sure what the word stochastic means, frankly. I think it just means an element of randomness. What does stochastic, what does the word stochastic mean? Non-deterministic? Yeah, well, of course, chaotic systems are secretly deterministic, but you can't follow them very long in time unless you have a degree of precision which is far beyond what's reasonable. I don't want to get into chaos too much right now. I will just tell you very quickly one other thing about chaotic systems, or the difference between chaotic and not chaotic. Both of them have the feature that the phase space volume stays the same. But that seems a little odd, because you would think that for systems which are chaotic, you know, just systems banging into each other in random collisions, not random really, but governed by the equations of motion, but nevertheless complicated enough that they seem to scatter all over the place, you would think that the phase space volume increases because after a while you know less and less about where the system is. Well, that's not exactly true. Here's the way it works. Supposing you take, all right, so the correct statement is that this little sphere in phase space will evolve, and it will evolve into something which may look more or less like a sphere, but it may also look, grow all kinds of complicated fibers and become very fractalated. I don't know, is fractalated a word? Probably not. It'll start to grow. Okay, now here's what you do. I want to put some more in. Etc. All right, now, if I literally mathematically follow the points, incidentally, this will be just as continuous as this. If you look at it under a microscope, you will discover that this phase space is completely continuous. Nothing discontinuous is broken off it or anything like that. But as time goes on, it tends to get more and more fractured like this. Let's just call it fractured. If you take each point goes to a definite point. If you follow the volume, you'll find the volume is the same. But now you can do something which is called coarse graining. Coarse graining means a purposeful decision to draw little circles or spheres around phase points, and roughly speaking, what it corresponds to is saying, I don't have enough precision to be able to distinguish points of phase space. Strictly speaking, I can only distinguish this little volume from that little volume, from that little volume, and that little volume. So what we do is draw little spheres around each phase point and follow the little spheres rather than the individual phase points. Follow the spheres, and what will happen is this sphere may go over here, the sphere may go way over here, This one may go way over here. This one may go way over here. But if we were to take the total area occupied by these spheres, I think it's pretty obvious that the total area will be much larger than the area that you started with if this thing branches out and fractalizes, and it is. So the coarse-grained following of the phase space allows the area to get bigger and bigger, and it does get bigger, yeah.
Okay, so that's why I was asking that question, because in order for those areas to stay the same exactly, it would have to be in some kind of a limit as a known to be random distribution. And what you're saying is because of the coarse graining, it's
Yeah.
effectively random.
Yeah, because of the coarse graining, it's effectively random. In other words, if you take the coarse-grained phase space, the nasty thing that happens is no matter how small the coarse graining is, if you wait long enough, points within one coarse grain here will separate and get far outside a coarse grain. Right? If the coarse grain is defined by little spheres. So
what were your second little spheres?
what's that?
The mapping from the first.
No, they're not the mapping from the first. No, the mapping from the, no, they're not the mapping from the first. They're just spheres in the phase space again. Spheres that you can distinguish by the coarse-grained apparatus that you happen to have. So the coarse-grained apparatus that you happen to have defines a coarse graining on here. And it's not the same as the coarse graining that would inherit by following this coarse graining. It's just what you can measure, what you can distinguish. And of course, what you can distinguish depends on the precision of your measuring apparatuses and so forth. But no matter how precise your apparatuses and your description is, no matter how small a coarse graining here, eventually points within a single cell here of this coarse graining will diverge and get outside the corresponding coarse grain description of what happens later. That's what happens to a chaotic system. Most systems are chaotic, of course. The non-chaotic systems, which sort of maintain their integrity without, in the coarse grain sense, those are rare and exceptional. Yeah.
The difference between points in a phase space, that's tracked by time?
Say it again.
The difference between points in the phase space when they change, are we looking at a change in time or change?
Yeah, change in time. Yeah.
When you say the area increases, what is it?
The area of the coarse grain, you take the original region of phase space, you figure out exactly what it does. And then in the original region of phase space, you draw spheres. If the original region is a nice, simple sphere or something like a sphere, then when you add up all of these coarse grain spheres, you'll get the volume of the original sphere back, pretty much. But now you take this tree, this very, very finely fractalized tree that it grows into, which may fill up this very big piece of this blackboard with very fine filaments, very, very close to each other. Okay? So, for example, if there are filaments extremely close to each other, so close to each other that the coarse graining sort of slops over the distinction between these different filaments, then the total volume of these coarse-grained green spheres will in general exceed the volume that you started with. Why? Yeah, it's basically just going to cover this whole, the whole tree there. Yeah, yeah. You just, yeah, yeah, yeah. So you just look at this picture with fuzzy eyes, and you see how big this region is. This region could be much, much bigger.
You can think of the thing as starting as a solid volume and then evolving by having it being invaded by other stuff.
Yeah, you can. lots of ways. The what?
That's right. Yes. The ball.
Yeah, you're counting everything within this little sphere here, even though the fiber in here may be much thinner than the sphere. But the fibers are so thin that your apparatuses cannot tell exactly where you are in the sphere. All you know is you're somewhere in the sphere. So at the end of the day, if you ask, where am I if I start in here? The answer to the question is, you're somewheres in here, in a much bigger region. If you had infinite precise control over either the mathematics or the measurement, then the volume of this fibered, ultrafine filamentary structure would be exactly the same as the original ball here. But you don't follow things that way. That's not the way you follow things in an experiment. You say, okay, I detect a particle somewheres in this phase region over here. I can't tell exactly where it is because it requires too much precision. So in that sense, the phase space volume does expand. Okay, it's called coarse graining. And it is, of course, the origin of the second law of thermodynamics. Okay, there's one other point that I should emphasize. I don't know when and if we'll come to it in a more thorough way. But the entropy of a system is a measure of the volume in phase space that the system occupies, the detectable volume in phase space. Meaning to say, if you know about a system that it's somewheres in here, you take that volume of phase space, which corresponds to the boundaries of the region that your knowledge tells you that the system, I'm getting tied up. You have some knowledge about the system. The knowledge of the system is that it's somewheres in here, in this volume of phase space. The entropy is a direct measure of that volume. In fact, it's the logarithm of that volume. Okay, essentially, now the system evolves, and what you know afterwards is that it's somewheres in here. You're not either clever enough or precise enough to be able to distinguish these fibers, so all you know is that the system is somewheres in here. The phase space volume is bigger afterwards than it started in the beginning because you haven't followed the details sufficiently carefully to know precisely, to distinguish this bit of fiber from that bit of fiber. That's why entropy increases. Basically, it's a statement that when the phase space fragments like this, you lose information not because information is really lost, but because you have a hard time following the system. It's a technological thing. You can't follow things with sufficient precision. Okay, that's Liouville's theorem. As I said, it is extremely fundamental to both classical mechanics and its evolution into quantum mechanics. What I wanted to do next, completely different direction, was to work out the equations of a particle. We have not studied very many examples, incidentally, you'll notice. I want to study the example of a particle moving in an electromagnetic field. There's one thing that's new in a magnetic field that we haven't encountered yet, and it's the existence of velocity-dependent forces. So far, the forces that we've imagined depend on where you are, but not how you're moving. When we said that there's a potential energy function, U of x, and we differentiate it to find the force, well, the left-hand side is just a function of position. So the force on a system just depends on where you are. There are forces in nature which depend on velocity. Magnetic field acting on a particle is a prime example. Incidentally, friction is also an example. Friction is an example where the velocity of where the force on an object does depend on its velocity. If it's standing still, there's no friction force. If it's moving, there is a friction force. Typically, the faster it moves, the larger the force. There's a fundamental difference between magnetic forces and friction forces. And the simplest way to say it is that forces due to magnetic fields, although they're velocity dependent, are derivable from a principle of least action. They have a Lagrangian formulation, there's a conservation of energy, and there's a Hamiltonian formulation. It's just that the Lagrangian and Hamiltonian have a new little twist to them that I want to work out now. Forces due to electric fields are no different than the forces we've already studied. I think I'll come back to electric fields. I want to concentrate on magnetic fields because there's a new phenomenon there that's interesting. All right. So what is the force of a particle if it's in a magnetic field? The magnetic field is called B. It's a vector, and it depends on position. B of x, the magnetic field. What is the force of a charged particle on a charged particle? V cross B. Well, actually Q times V cross B, where Q is the charge of the particle. Velocity cross magnetic field. It's a vector, the cross product of two vectors. Both of these are vectors. This is the velocity of the particle. This is the magnetic field. And so it says, everybody know what a cross product is? I assume everybody more. That means yes or no?
Something to do with the thumb.
Yeah, right. Right, let's see. Right. Something to do with the thumb. I'm going to assume everybody knows what a cross product is, although I will define it. Okay. So let's define the cross product right now. The cross product can most easily be defined through its components. V has three components, x, y, and z. B has three components, x, y, and z. The cross product has three components. Here's the rule. The z component, let's forget Q here and let's just write the rule. The z component of this, let's call it the z component of it. V cross B, the z component of it, is equal to Vx By minus Vy Bx. I remember one of them. I remember the z component. And then if I want any of the other components, I just cycle. Z goes to x, goes to y. So the next one would be x. V cross B, the x component, and I cycle. X goes to y, Vy, y goes to z. Bz minus Vz By. And the last one, V cross B in the y direction is equal to x, y, z, y, z, x minus V x, B, z. Did I get that right? I think I got it right. Okay, that's the definition of a cross product. Now we need one other concept. We need the concept of the vector potential. The vector potential is simply a way of writing magnetic fields. But you would think, well, if it's just a way of writing the magnetic field, why not just use the magnetic field? And the answer is you cannot write the mechanics of a charged particle just in terms of the magnetic field. You need the vector potential. You can, of course, write the mechanics F equals ma, but you cannot write a Hamiltonian, you cannot write a Lagrangian, you cannot write even an expression for canonical momenta. You need an auxiliary quantity called the vector potential. And the vector potential is just defined by the condition that the magnetic field is the curl of the vector potential. Let's write down what curl means, because we'll need it later. The vector potential is also a vector. The magnetic field is a vector. The vector potential is a vector. What's special about things which are curls of other things? They have no divergence. And the magnetic field is a thing which has no divergence, and that's why it's convenient to write it this way. But for our purposes, let's imagine that the vector potential is something fundamental that we begin with, and that the magnetic field is a derived quantity. We're going to see that the mechanics of a charged particle is best written in terms of the vector potential, not the magnetic field. Okay, let's write down the definition of cross product. The cross product, again, can be defined by its components. Del cross A, the z component of it. Now, it's basically the same thing, except wherever you see a v up there, wherever you see a b, stick an a, and wherever you see a v over there, put an upside down delta. All right, so this just says that this is, what does delta mean? It just means the collection of three derivatives. Delta x, delta y, and delta z are just derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. I assume you all know that kind of thing, a little bit of vector calculus. But let's just write down exactly what this means. This means derivative with respect to x of a sub y minus the derivative with respect to y of a sub x. And then cycle it down. Del cross A, the x component of it, is the y derivative of az minus the z derivative of ay, and just cycle it down. X goes to y goes to z goes back to x. I won't write them all down. So we can now write that the force on a charged particle due to the magnetic field is the charge times v cross b, which is also the charge times v cross the curl of A. I'm going to bore you a little more with this by writing out the individual components, by writing out the z component of force here. It's a little bit tedious, but we'll need it. We'll need the expression for the z component of force explicitly in terms of the vector potential. So let's write it out. This is just an expression, this is just an exercise in substituting. All right, I want the z component of the force. F sub z is equal to the charge. Now, the cross product. All right, we have the cross product. Where is it? We have the z component of v cross b. That's vx by minus vy bx. But now let's just substitute in for by. Where is it? Oh, brother. This is q. Vx. Now, go to by is dz ax minus dx az. That's the first term, minus vy times bx, which is dy az minus dz ay. Well, this is a fairly complicated expression for the z component of force, but if you know the vector potential, you can work out what this is. It's just some vector field. You can multiply it by the velocities, and you can compute the force, the z component of force. If you want the other components, again, you just cycle. The x goes to y goes to z. You just cycle through. All right, that's the force on a particle, and the equation is just Newton's equation, F equals ma. But now the new thing is that the acceleration doesn't only depend on the position, it does depend on the position through the position dependence of a, but it also depends on the velocity. So these are called velocity-dependent forces because they depend on velocity. All right. We want to formulate the theory of a charged particle moving in a magnetic field in the Lagrangian or Hamiltonian form. Not obvious that we can do it. It is not obvious that this is of the form that allows us to have a Hamiltonian, a Lagrangian, and so forth, or an action principle. The easiest way to confirm that is just to make a guess at what the action is and then follow it through. The new thing in the action, well, first of all, we do expect that if the electric charge was 0, that there would be the usual terms, right? So let's write the action. Let's make a guess for the action. The integral of the Lagrangian dt, well, first of all, guess has the usual mv squared over 2 dt, where v squared means the sums of the squares of the x component, y component, and z component of the velocities, the usual thing. This is what we would do for a free particle, and if the particle has no electric charge, it doesn't feel the magnetic field. And then there's another term, and the other term is as simple as it could possibly be. We take the orbit of the charged particle, we break it up into little segments. Each segment we call dx, also dy and dz, but let's just abbreviate it by calling it dx. Each little segment defines a differential displacement in dx, dy, and dz. The added term that's first of all proportional to the electric charge. If there's no magnetic field, then obviously there is no additional term, even if there is an electric charge. The extra term is related to both the charge and the magnetic field, but it's related through the vector potential. Where's vector potential? Oh boy, did I erase the most important equation? I did. Okay. I assume you all memorized what V cross B looks like in terms of the vector potential, and you'll recognize it when I write it down. I didn't mean to erase it. All right, what can you write down? It's going to have the vector potential in it. So let's call it A sub I. The simplest thing you can write down is the integral, the line integral of the vector potential dotted into the differential displacement dx. In other words, what this means is every place in space you have a vector potential. As the particle sweeps out through its trajectory, there's a contribution to its action from each little differential displacement here. And the contribution to the action is just take the dot product of the vector potential with the displacement. In other words, the component of the vector potential along the direction of the displacement, and add them all up. Very simple prescription. How do I know that's the answer? Well, I know that's the answer because it was written down in the early parts of the 20th century and I learned it as a student. Yeah, dxi, good. Or you can just write a dot dx, where you can think of both a and dx as little vectors. Well, one is a little vector, the other is just a vector. All right, a dot dx can represent the dot product of the vector potential with the differential displacement. How do you know what the units are? Do you know what the units of A are and what the units of Q are?
Like, you could work backwards and you'd expect to see a time in there.
A time.
And V squared, so the
Hmm?
V squared is, the first integral has a.
But how can you tell me what the units are unless we know what the units of Q are?
Okay.
Or A? How do we know what the units of A are? Well, the units of A and the units of Q, obviously the combination Q times A is the important thing. And the combination of Q times A has units that are required to make this have the same units as that. What are the units of an action, incidentally? Or momentum times position. Sorry, momentum, yeah, momentum times x. No problem, you can always give Q the right dimensions. This is correct in some appropriate choice of units. This is correct. And it depends on the conventions. In some conventions, there are pi's floating around or speeds of light, but you can set them all equal to 1. And since I'm trying to describe a phenomenon rather than a numerical effect, let's just set all the numerical constants equal to 1 or to absorb them into the electric charge here. Okay, now this is, yeah.
Convert that to an integral in dt by.
Yes, that's exactly what I was about to do. This does not have the usual form of an action, which depends on velocities and positions. The A's depend on position as a rule, but what is this dx here? Right? All we have to do is divide and multiply by dt. Dx by dt, that's just the x component of the velocity. Right? So we can also write this as a dotted into the velocity integral dt, or I can write it in terms of components a sub I x sub I dot dt. And now we see the usual form, what's that? Sum over I. Yeah, sum over I. All right. So we see, and this of course is also x sub I dot squared. Sum over I. I'm not going to write it. All right, so we have then a typical Lagrangian. We can write out now what the Lagrangian is, and it depends on position and velocity the way any respectable Lagrangian would. Lagrangian for a particle in a magnetic field is 1/2 the mass of the particle times x sub I dot squared, where I goes over x, y, and z, sum. Plus q, the charge of the particle, x sub I dot times the vector potential a sub I. What's the next step? The next step is to prove that the equation of motion for this object is F equals ma, with the right-hand side being, where is it? QV cross B. F equals QV cross B. If we can do that, if we can now take the Lagrange equations, here's the Lagrangian, take the Lagrange equations and see if we can prove that the force on a particle, this is equal to mass times acceleration, that this is equal to QV cross B. If we can do that, then we're finished. We've found the Lagrangian formulation of particle in a magnetic field. So this is now an exercise in just plugging it through. I could tell you to go home and do it, but let's do it. Let's just carry it out. There's one curious thing coming up that we'll see in a second. First of all, what is the canonical momentum piece of x? Well, it's the derivative of the Lagrangian with respect to x dot. So let's take the x component. I now mean the x component. We could write down y and z also. That's going to be m x dot from here, usual thing, normal momentum, but then there's another term, plus q a sub x. And of course, the same kind of thing for py and pz. So we have a system now where the canonical momentum is not just m times v. It's m times v plus something proportional to the vector potential. Sometimes m times x dot is called the mechanical momentum. It's sometimes called the mechanical momentum, meaning to say, it's meaning to say nothing other than that it's mass times velocity. And the whole thing is called the canonical momentum. Okay. All right, so that's one new thing here. We see something new, that there's a discrepancy between the canonical momentum and what we naively think of as momentum. Okay. But now let's work out the equation of motion. Let's work out the z component. There's three of these, but let's get to pz is equal to m z dot plus q a sub z. I'm going to work out the z component of the equation of motion. What is it? It's the time derivative of the momentum. I'll just write down over here. d by dt of dl by dz dot is equal to dl by dz. dl by dz dot, that's just pz. Okay? So we have to take the time derivative of this thing here. Let's write down the time derivative. It's m z double dot. That's mass times acceleration. And then there's another term in the time derivative of pz. It's plus q times the time derivative of az. Now, in a moment, we'll come back and work out what the time derivative of az is. But let's go to the right-hand side of the equation. The right-hand side of the equation is the derivative of the Lagrangian with respect to z. What is it that depends on z in here? X dot doesn't, or z dot doesn't depend on z. A. And all of the a's, ax, ay, and az, all depend on z in general. So let's go through them. Q. Now, the first term here would be x dot times a sub x. So we would get a term which would be x dot times the derivative of a sub x with respect to z. Remember, we're taking the derivative of the Lagrangian with respect to z. The only thing that depends on z are the three components of a. Let's start with the x component. X dot times ax, and differentiate it with respect to z. The next one is plus y dot times the derivative of ay with respect to z. And what's the last one? Z dot times the derivative of a sub z with respect to z. Okay, all I did was differentiate all three terms here with respect to z. Each one of them depends on z through the components a. What about the left-hand side? What do I do with a sub z dot? Let's suppose, incidentally, that it's just a static magnetic field. Magnetic field not changing with time. It's just a fixed magnetic field. Does that mean that this is zero? If it's a fixed magnetic field? No. No, because the particle moves through the magnetic field. I don't mean, when I say it's a fixed magnetic field, I don't mean it's the same everywhere in space. I mean it doesn't depend on time. Magnetic field varies from place to place. Particle moves through it, and because the particle moves through it, there's a time dependence of the magnetic field, of the vector potential, at the point of the particle. So how do we calculate that? Well, we simply write m z double dot plus q. Now, az depends on x, the AZ by dx, times x dot, plus the AY. Sorry, what are we doing here? Yes, sorry, the AZ, sorry, AZ. We're calculating AZ dot, which is the derivative of AZ with respect to x, times the time rate of change of x, plus the AZ by dy times y dot, plus the AZ by dz times z dot. That's equal to what's in the bracket over here. Equals this. Okay. I'll let you stare at it for a minute. Remember, the right-hand side came from explicitly differentiating the Lagrangian with respect to z. The left-hand side came from differentiating with respect to t. But notice they have similar form. Each one here has a velocity times a derivative of a on both sides. So maybe they combine together in some nice way. Well, first of all, you'll see that this term and this term are the same. Z dot times the AZ by dz. They're the same. So they cancel. Let's get rid of them. Now what's left? Let's look at what multiplies x dot. X dot has the AX by dz, and then when we shift to the other side, it will have what? The AZ by dx. So it's going to have, let's move this over. Now I forgot what it was. Plus y dot, what was it? The AY by dz? Yeah. Partial AY with respect to z, right? Yeah. Okay, now what the term which multiplies x dot, when I transpose it, it's going to have minus the AZ by dx. Oh, that's starting to look familiar. And when I transpose the term that has y dot in it, that will have minus the AZ by dy. I've transposed this term over to the right-hand side, and I now have mz double dot, or mass times the z component of acceleration, is equal to this mess over here. Well, what is this mess? This mess is not so complicated. It's got linear terms in the velocities, and what are these objects? The magnetic field, the curl of the vector potential. In fact, this one is AX1, I think this is BY. Is it BY or minus BY? And this one I think is minus BX. The x dots and y dots are the components of the velocity. If you go through it, or just go back in your notes to where I wrote it down in the beginning, this is just the z component of v cross b, velocity. Yeah, okay. Right. Vx times dz ax minus dx az, and so forth. Yeah. Okay, so you see that, first of all, there does exist a Lagrangian formulation. Here it is for particle in a magnetic field. You need to know the vector potential. First question, is the vector potential unique in terms of the magnetic field? No. You can add things to the vector potential. We'll come to that, but not right now. But if you know the vector potential, or you know a particular expression for the vector potential, then you can write down the Lagrangian. The Lagrangian depends on the vector potential, but the equation of motion only depends on the magnetic field. So even if there is an ambiguity in the vector potential, it doesn't affect the equation of motion itself. Okay. Now, we have an example of a velocity-dependent force, a force which is V cross B. It's almost like a friction force. It is different. The friction force acts along the direction of the velocity. Okay? If an object is moving in this direction, the friction force is along the same axis. What about V cross B? Does V cross B act along the direction of the velocity? No, because V cross B is perpendicular to both the velocity and to B. So, this is a big difference. A big difference whether the velocity-dependent force acts along the direction of velocity or perpendicular to it. If it acts along the direction of velocity, it will obviously have the effect of either slowing it down or speeding it up, depending on which way it's acting. All right? But if it acts perpendicular to the velocity, it'll simply change the direction of the velocity if the force is perpendicular, and it won't change the energy. So energy conservation we can work out now. We can work out what is the expression for the energy. We do that by calculating the Hamiltonian. And when we've calculated the Hamiltonian, we then have, from previous theorems, the theorem that says that energy is conserved. All right? So we can work that out. Let's work it out. I think that'll just about take us to the end of the hour. Oh, excuse me, there's something I need to tell you. I won't be here for the next 2 lectures. Now, I would like to make up one of them. I think the question is, what is a good time? It could be this week yet, but it can't be next week. And it could be the week after, but not on Monday. Yeah, we can do it this week. Does that work out for people? If we were to do it, say, Thursday? Friday is a bad day for me. Or we can put it off. We can put it off till I get back and just double up the week that I come back. I'll be gone for. Should we wait until? Thursday? How many cannot take it Thursday? Well, that's almost half the class. Supposing I were to put it off, I'll be back on the 11th. Now, the 11th is probably a Monday. No, 11th is a Tuesday. Yeah, I was thinking about Wednesday. The 12th, I think it is? Is it 12th or 13th? Does that work? No. I know that. Well, we can stay on Monday, and but yeah. No, we'll continue. We'll continue, but at some point we run into the next quarter. I mean, you know, like playing. You know, points have to move rigidly. You can't. Well, we could do that. Another thing I have to do is I'm supposed to fill in the missing lecture from the first lecture. I was thinking of doing that this week, but no. We didn't miss a lecture, but they didn't film it. Right. What's that? No, that doesn't have to be. No. I'm happy to this is fun for me. I just do it for the fun of it. No, I intend to keep going until sometime near Christmas. But we will miss the next 2 lectures, so I thought I would try to make up one. What's that? Yeah, 2 Mondays. But then we'll be back on Monday. Well, we will be back on Monday, and we'll see if we need to fill in with another lecture. We'll just figure out at that point when to fill in.
Yeah, we're already scheduled for the 17th, so the next Monday is Christmas Eve.
Well, I don't think we'll do Christmas Eve. That's
So that means we sort of run into the wall there.
yeah. Yeah, well, look, why don't we just decide this when I get back on the 17th. We'll see when we can fill in an extra lecture. And I think that'll pretty much bring us to where we want to be. I mean, I'm pretty comfortable. Yeah, 3 weeks? Yes, 3 weeks from today. Right. 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 Next lecture is the 17th. Okay, let's try to just finish up what I was talking about here. I think I finished. Energy, yeah. Okay, let's do energy. So all we have to do is calculate the Hamiltonian. Incidentally, I'm assuming that the vector potential has no explicit time dependence. In other words, equivalently, that the magnetic field is constant in time. In that case, the Hamiltonian will be time independent, and there will be a conserved energy. The conserved energy is surprisingly simple when expressed in terms of the velocities, a little more complicated when expressed in terms of the momenta. So let's work it out. Let's first calculate P sub x, as we saw before, was mx dot plus qa sub x. Same thing for y and z, and I won't bother writing them down separately. Okay, the first thing we have to do when we calculate the Hamiltonian, actually we don't need to. We can just, let's calculate it not in terms of p, but in terms of x dot. Let's first do it by calculating it in terms of velocities to see what the expression for energy is in terms of velocities. All right, so what do we have to calculate? We have to calculate p sub x, x dot, plus p sub y, y dot, plus p sub z, z dot, minus the Lagrangian, right? That's the definition of H. Take each momenta, multiply it by the corresponding velocity, and then subtract the Lagrangian. That's a very general rule that we derived. All right? If I plug in for the p's their expression in terms of velocities, I'll have an expression for the energy in terms of velocities. That won't be good for Hamilton's equations, but it will be good for telling me what the energy is in terms of velocities. So let's do that. Let's do that first. P sub x times x dot. That is m x dot plus q a sub x times x dot. Likewise for y and z, and I won't write them out. Then we have to subtract off the Lagrangian, minus L. So subtracting off the Lagrangian means subtracting off minus mv squared, or mx dot squared. I'm concentrating on the x term. Mx dot squared divided by 2. And then what else? Minus q x dot a sub x. Well, that gives me mx dot squared over 2, the usual thing, no difference there. And look at this, qax x dot minus qax x dot. They cancel completely. So the expression for the energy is exactly just the original kinetic energy, just mx dot squared over 2. Likewise for y and z. The magnetic field does not contribute to the energy when expressed in terms of velocities. It's just 1/2 mv squared. End of story. Now, why is that? Why is that? That's equivalent to another statement. It's equivalent to the statement that magnetic fields do no work. What's that? Yeah, that's right. It's because the force is perpendicular to the velocity. So when a particle moves in a magnetic field, the force is perpendicular to the velocity. The force being perpendicular to the velocity means that the magnitude of the velocity doesn't change. Right? A force perpendicular to a velocity deflects an object but doesn't change its velocity. And so as the particle moves along, its direction may change, but its speed doesn't. So it's the original expression for its energy in terms of mx dot squared is just the full energy. Magnetic fields do no work, which is the same statement as a statement that the energy, when expressed in terms of velocities and so forth, is exactly the same as it was in the first place. 1/2 mv squared is conserved. And you know how particles move in a magnetic field. For example, if there's a uniform magnetic field into the blackboard, particles move in circular orbits with uniform speed. So the kinetic energy is conserved. That's statement number one. But in this form, you cannot use the Hamiltonian to write down Hamilton's equations. You have to express it in terms of the momenta. But that's easy. All we have to do is solve for the x dots in terms of the momenta. That's easy. X dot is just p sub x minus q a sub x divided by m. So we can write down immediately what the Hamiltonian is in terms of p's instead of in terms of x dots. And it's just equal to p sub x minus q a sub x squared over m squared. Over 2m squared, excuse me. I've just substituted for the velocity their expression in terms of the momenta. Yeah? No, it doesn't. It accelerates. Oh, it does. It does. It does. But radiation is a higher order effect that is only important when the particle is, yeah, it does. It certainly does radiate. Right. But thus far, we have not even tried to think about radiation. In order to understand radiation, we would have to formulate Maxwell's equations and formulate them in a Hamiltonian form and discover that the radiation field itself has energy. Yeah. Right. So, yeah, this is the radiationless approximation. Right. You mean these? Yeah, sure. Absolutely. Plus z term. Right. So it's a little bit odd and a little bit surprising that when expressed in terms of velocities, the energy just doesn't change. But when expressed in terms of canonical momenta, the expression for the energy does change. And now, if we applied Hamilton's equations to this expression here, we would again get precisely the same equations of motion. What's that? Yeah, all you do is replace the canonical momentum by the momentum minus q a sub x. In other words, this is just a mechanical momentum here, the mx dot term. The mechanical momentum and the canonical momentum differ by q times a. The energy is just mx dot squared, so it's just a mechanical, it's just the square of the mechanical momentum. But you substitute the canonical momentum if you want to do Hamilton's equations. So here's an exercise. Take this Hamiltonian, work out Hamilton's equations, and check that you get the same equations of motion that Mass times acceleration is equal to v cross b. That's a homework assignment. Okay, good.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.